Hello class, Professor Dre here for another one. Here we got the week 1 worksheet for Calc 2. First problem, we find the derivative. Find the derivative y equaling 2x plus cosine of 5x to the 7th power, all to the negative 3rd power. So there's quite a bit to break down here in terms of the chain rule and what kind of rules we are using as we go. So let's go through it and try and understand it. And realize that you can always stop this video, try it yourself, and see what we come up with. All right, let's go. So I want to take the derivative of this, and so following the chain rule, right, we take the outsidemost function. What's the outsidemost function? This negative 3 power. So it's a power, right? I'm not considering anything inside to be anything that's there. So this stuff doesn't really matter. We'll do that later. So I might do that at a different color, but so let's underline it in green. There we go. Beautiful. And we're going to do this in purple. So how do I take the power rule? So something raised to a power of negative 3. We bring down the power. So taking the derivative. So bring down the power, and then we're going to keep the stuff the same. We don't touch it. So for those of you coming from my Calc 1 class, you know that's a thing. We don't touch it. We don't touch the inside function. We leave it completely alone, right? So that's the inside function. We leave it completely alone. We're doing the outside function. So we brought the power down, negative 3. We're going to subtract 1 in the power to make it negative 4. So well, now we have finished that part. So now we want to look on the inside of this and try and work that problem. And so when I'm doing these chain rules, I like to start a bracket, right? We multiply by the derivative of the inside. So we're going to start a bracket, and then we'll finish it when we know we finished the chain rule of this stuff on the inside. All right, so let's go for it. So the derivative of, let's go for 2x, right? 2x, derivative of 2x is 2, plus, now I'm going to do the derivative of this stuff right here. So this is cosine 5x, all raised to the 7th power. So there's another chain rule going on there. So I am done with this piece, right? This piece's derivative is done, but now I'm taking the derivative of this whole thing. So now I'm going to look at this bit, and that takes another chain rule. I have something raised to the 7th power as the outermost function. So let's do that power rule again. I'm bringing down the power, so that's 7. I'm going to leave alone. I'm not going to touch it, right? Don't touch the inside function. So cosine of 5x. So all raised to the new power, which we just subtract 1 from that 7 to get 6. So I am not done with this piece's derivative, right? Because this takes a chain rule. So let's use red, right? This takes a chain rule. So when I multiply this by its chain, right, it doesn't get multiplied by this. So a lot of students will finish this off right here, because it seems like I'm done. No, I'm not done. I'm not done with this piece. So I'm going to multiply this piece's derivative right next to it. So I'm going to start a new chain right here. I didn't close off this stuff, right? I don't want to close it off, because then that would be multiplied by the 2, and that is not true. So, all right, so now we're taking the derivative of cosine of 5x. Cosine of 5x, the derivative of that is negative sine of 5x. Don't touch the inside function, right? And that is the derivative of that inside stuff, right? But I'm not done yet, because now I have another derivative. What color do I use? Let's use blue for this 5x. What is the derivative of 5x? So the derivative of 5x, so I'm going to go ahead and start a new one just to kind of see how it works, right? So taking the derivative of 5x, well, that is just 5, right? I have finished that thing's derivative, right? There's no other inside function of this thing. That is it. I am done with that piece's derivative. Which means I am done with the red part's derivative, which means I am done with the green part's derivative. And that is my derivative altogether. Yes, I can kind of simplify some things. Maybe I can bring this 5 out to front, the negative out to front here, and multiply by that, making that negative 35. That's not a big deal, right? I have this negative 3 out there too. I don't know. We can push this down to the bottom. That's not the point of this. The point of this is to make sure we understand how to work chain rule and how best it's done. And this is one of my best ways to do this. Again, all right, well, I said this in Calc 1, I didn't say this here, but right, when I do these in one fell motion. There are many ways to do these step by step, right? But you can look it up yourself. If you're not understanding the way I'm doing it, let's look up some YouTube videos, let's look up some things online to try and find out how best to do this. Let me pause the video and go on to the next one. Okay, number 2, let's go ahead and find the derivative of y equaling 3 to the power of tangent to the inverse tangent, I should call it, right? It's not to the power of -1. So of 3x to the 4th. So all of that is in the power. So hopefully that's apparent with what we have there. So another chain rule going on here. So our outermost function is 3 to whatever power we have, 3 to the u, we might be able to call it. So if I wanted to take the derivative of 3 to the u, well, that would be y prime would equal ln of 3 times the 3 to the u times du, right? Or the u prime, let's call it. So, and we can do that, right? So there's the chain rule, right, embedded within this exponential function. So let me get rid of that and let's go for it here. So I'm going to do it in one fell swoop again. So we are looking at 3 to the power, so an exponential function. So y prime will equal, so I'm going to do the ln of 3, because I like it out front personally. You don't need parentheses around it because it's kind of said, but what comes after is not in the ln or the natural log, right? That is an L, not an I. So, and then we have the next piece, the 3 to the u, which is 3 to the tangent inverse of 3x to the 4th. And then we have times the derivative of this stuff, right? So the times the du is the next part. So we're going to take the derivative of that piece now. All right, so taking the derivative of this, tan inverse, right, is a really strange derivative, right? An even stranger integral from there to get. So I have 1 over 1 plus x squared. So x squared, the stuff inside squared, this stuff being squared right here. So, right, I'm going to look at this right here and I'm going to square it. So that would be 3x to the 4th, and I'm going to square that stuff. So we can write it like this, and we can simplify it later if we want to, right? So that was the inside function, right? So we just did the tan inverse. Now we need to do the innermost function of this inside function. So so there we have 3x to the 4th. I need to take the derivative of that. So let's do it in blue. So, right, and I should have started this, right? I should have started this right here. A lot of students might think it goes right next to that little piece down there, but this is the derivative of the tan inverse, this whole piece, right? So we did that piece. Now we're timesing that by the derivative of the inside, the 3x to the 4th, all right? And I used incorrect coloring here, so this should be green, right? So, and then now I'm switching to blue, so now I'm going to have blue right there. All right. So what do I got? So the derivative of 3x to the 4th is 3 times 4, which is 12x to the 3rd now. And I am done with that piece's derivative, which means I am done with the tangent inverse's derivative, and it means I am done altogether, and that is that. So there is that piece's derivative. We can simplify this a little bit just to kind of simplify it up a little bit, because I do have that square in there and it's bugging me, right? And that's kind of what simplification is about. in this case, we are going to start using these things and abusing them. And so we need to be able to kind of manipulate them a little bit easier. So it's all about how we want to do it. I might throw the 12x cubed in front just because of my OCD that I need to do this with. I might throw all that stuff on the bottom into the bottom down there and everything else in the top, right? So 1 plus that stuff being squared, which would, if I square it, it would be 9x to the 8th power. 9x to the 8th power, and there is my derivative. All right, let's save that. We're going to pause here. Pause recording. Okay, so now going on to integration, right? The opposite, essentially, of differentiation, right? Of derivatives. So I want to take the integral of x squared over the square root of x minus 9 dx. So, right, the dx tells us what we're taking the integral with respect to. So that way we know we're supposed to look at the x's here. Sometimes in this class in particular, we will start mixing up the letters, the variables, and some of the variables we'll consider as constants because we'll be taking the derivative with respect to x or with respect to y or with respect to a or b. We have to be very cognizant of what we're taking the derivative with respect to in this class. All right, so let's go for it here. So I want to take the integral of this thing. Did I say derivative? So the integral. Integral is what we focus on a lot more in this class. All right, so let's go for it here. So this to me looks like a u-substitution method, and so what we can do is there's a few things we can do with this. So I think usually what I say is when we're doing this, we're looking for things in the denominator. Sometimes we can let u be the whole thing in the denominator, or radicals, and we have both here, or the whole radical, we can set u equal to the whole radical, which is the same as the denominator, or the things under the radical. And it really just becomes a choice of how you like to do it. And we have to have that ability to say, the mathematical confidence in ourselves to say, all right, I'm going to try it. If it doesn't work out, no biggie, let me try another method. All right, so there's a few things we can do here, and if hopefully we notice that it's going wrong, and we can back up and try it and do it again a different way. All right, so I'm going to try this one. It's been a long time since I've done this problem, but nonetheless, I'm going to try this and see how it goes here. I used to just make it the stuff under the radical, and then some of my students have shown me in the past that really it's pretty nice to use the radical, and let's see what happens. So, and this is going to be a cool one. I can see it already. All right, so I'm going to take the derivative, right, of u. So as u-substitution, I let u equal something, and I take the derivative or the du of it. Right, this is how I do it. So I'm going to take the derivative of the 1/2 power. So right, there's an invisible 1/2 power around all of this. And so it's kind of a chain rule, but the derivative of the inside is just 1, so it really doesn't matter too much. So taking the derivative of that, I'm going to get 1/2. My power is 1/2. I bring it down. Right, and then I have 1/2 power up here, so I'm going to subtract 1 from it, so I'll get negative 1/2. And then I can't forget my dx, right? So I'm taking the derivative, it's kind of that derivative of x, right? The derivative of this piece, it's like a little chain rule that happens there to kind of help you remember. This is important because we are trying to ultimately replace the dx, and that is the ultimate goal of u-substitution. Is the one thing you have to do is get rid of this dx. Right? Sometimes these other things will fall out as we get rid of the dx. So let's see what happens here. So I'm gonna just rearrange this a little bit, noting that I have a negative exponent. So I'm gonna kind of pull things out, and I'm gonna get this. I'm gonna do a fraction here. So that 2 kind of goes in the bottom of the fraction, and so does the radical. Right? I'm gonna change that 1/2 power to again a square root of x minus 9, and I still have the dx there. And so now I'm looking at this going, I have everything right there listed right here. So I'm gonna have to undo that circling, but right, that's that right there. And so where this is in the bottom, that's in the bottom. So I can replace that stuff with that. But I still have this 2 there. So let me just do one little step. I'm going to multiply by 2. I get 2 du is equal to this thing, 1 over the square root of x minus 9 dx. Yeah. So now I can replace this I can replace all this red stuff here with this 2 du. So, so let me go ahead and do that so we can see what we have. So we're getting there. So I'm going to come down here. I'm going to have, I still have that x squared at the top. Not sure what I'm going to do with this, right? But that whole bottom kind of goes away, right? All that red stuff, sorry, I don't know why I did that fraction. All that red stuff kind of goes away, and I replace it with, let's use red here, 2 du, right? From this piece, 2 du. So I'm replacing all that right here with the 2 du. I'm subbing it in, right? Because they are the same, the way I set this up. All right, so well, I know I can do the 2 outside, so let's just do that. So can I take the integral here? No, because I have an integral I'm taking with respect to u, and I don't have any u's over here. But this is a relationship in terms of u. I just have to figure out what this is in terms of u. So let's go for it here. So let's bring this over to the side. I'm going to solve for x. So let's do that. So u equals the square root of x minus 9. How do I get rid of that square root? I'm going to square both sides of the equation. So I get u squared equals x minus 9. Let me add 9 to both sides. I'm going to get u squared plus 9 equals x. I have kind of one more thing here, is that I'm really looking for x squared. So let me square both sides. Let me just do that. So because I want that x squared, I can plug this in there, right, and say, okay, I'm going to square it here, but why not simplify this thing over in this area? So I'm going to square both sides of this to get that x squared going on. So I got, and then I'm going to FOIL out this process, because this is u squared plus 9 times u squared plus 9. If I FOIL that out, I'll get u to the 4th plus 2, I'm sorry, 2 times 9, which is 18. I'm using a formula for this squaring process of a binomial. So plus 9 times 9, which is 81, equals x squared. There is my x squared. Now I can replace, in terms of u, now I can replace it back in, and why not bring the 2 in now, just to not confuse me out there. So I'm going to bring the 2 in as we do this. I'm going to do 2u to the 4th plus 2 times 18 is 36 u squared plus 2 times 81. Oh, can I do the math? 162. Yes, I can. du. And let me throw some parentheses to make sure we understand what happened there. So I just did all this. Everything's in terms of u. Look at that. Beautiful integral. It is, right, just a polynomial that we can now use our integral definition, our integral rule for a power function. So, right, so to do that, I'm going to have 2u, my new power is going to be 5, I'm going to divide by 5. I'll have 36 u to the 3rd power, I'm going to divide by the new power, which is 3. And then I'll have 162 u to the 1st power, divide by 1. I don't need to do that. And don't forget it, plus c. So am I done? Can I box it here? No, because I have this in terms of u, but we know what u is in terms of x, which is the square root of x minus 9. So let's just replace that now. So I got 2/5. I'm going to kind of simplify as I go. We're going to do the square root of x. Is it minus 9 or plus 9? I forgot. Right, it is minus 9. There, I see it right above there. Minus 9 to the 5th power plus 36 divided by 3 is something. It is 12. 12 and u cubed. That would be square root of x minus 9 to the 3rd power plus 162 times the square root of x minus 9. So if you did it with plus c, then there is my answer. And if you did it with u equaling x minus 9, then you would have gotten the same thing, but maybe with half powers, like 5 halves here, right, which is the same, and 3 halves here, which is the same, and 1 half here is usually what happens when you do that. But it's the same thing. This I like a lot better. It usually takes up less work there, but maybe more work in the front lines. All right, so so we did it with the square root. All right, there we go. Let's move on to the next one. Okay, so number 4, find the integral of e to the 4x times the fifth root of e to the 2x minus 4 dx. All right, so let's do this. I'm seeing a little pattern. So there's a radical again, but I don't have the derivative of that radical. Before I did have the derivative of the radical in the previous problem. So let me show you, right? So when I did this pieces, when I looked at this, I said, oh, look, 1 over that square root is basically the derivative of that. And so I see that piece. So looking at this radical, I'm not going to make the u be the radical because I don't have the derivative of that piece, is what I'm saying. So, but what if I were to make it this stuff inside the radical as another option there? So let's let u equal e to the 2x minus 4, that whole thing. And let's see what we get. So I'm going to take the derivative of that, right? Again, dx is the main thing we need to absolutely replace no matter what. It's the other stuff we need to see if we have to replace it or not. So du is equal to 2e to the 2x. Sorry, I'm using chain rule there. So so the derivative of negative 4 is just 0. So chain rule, right? The derivative of e to the something is e to the something times the derivative of that something. So the derivative of the power is 2. So I just kind of did it really fast. Oh, I forgot the dx, right? Which is the derivative of really 2. 2x is the derivative of that is 2dx, we should say. All right, so now we have this, right? Which I kind of have this piece right here, right? So I have that, but it's like squared, that piece. So and so there's a bit there, and so I need to replace this, right? So I guess maybe what I could do is kind of force things to happen for myself, and let's see what we have replaced. So I know I need to sub in this stuff. So I don't have the 2, so let me kind of divide out the 2, I guess. Divide out the 2, the 1/2 here. So we get that 1/2 du is equal to e to the 2x dx. Let me just rearrange this integral so you see it. So I got e to the 4x is e to the 2x times e to the 2x. So what that allows me to do, since it's multiplication, is I can rearrange it and put one of those kind of with the other one. I just want you to be able to see it. You don't have to do this kind of stuff. This is just kind of for explanation purposes of me saying, hey, look, right, that can go over here with the dx, and there is this right here, right? And I can replace this with that. So, which is what I have to do, right? So what do I get? I get the integral of e to the 2x, whoops, fifth root of e to the 2x minus 4 times this 1/2 du. Let's pull the 1/2 out front. Du goes right there. There we go. Replace the dx. That's the thing we have to do no matter what. So let's go for the next step. So I clearly cannot do this integral still because I have du out here and I have x's in here. This one doesn't even look like an x, so let's make it look like an x. There we go. All right. But I have ways to replace this thing because I have this piece right here. So I have this e to the 2x, right? I have this right here. That's u. So I can replace that u there, but I'll still have this e to the 2x. But e to the 2x is just u plus 4, right? So if I solve this thing for e to the 2x, so I get add 4 to both sides, and I get u plus 4 equals e to the 2x. And I can sub that in for e to the 2x, and then I'll have everything in terms of u, and let's see what happens. So e to the 2x there that's left there is u plus 4. I don't want to sub in now down here, right? I don't want to use this anymore because I already did it. right? I don't need another du. If I get another du, we're going to du squared. I have no clue how to do that, right? So we do it once and we're done with the dx and we got rid of the dx. All right, now we got e to the 2x was this u plus 4, and then I have this fifth root of e to the 2x minus 4, which is u. I have the fifth root of u, du. Look at that, everything's in terms of u. This is a one-term thing underneath the power. It's the 1/5 power, so I can think of this as 1/2 integral of u to the 1 power plus u to the 1/5 power will be u to the 6/5 power plus 4 to the 4 times u to the 1/5 power. And then we have du on the outside of this. So let's go for it. I see power rules all over the place. So this is 1/2 times u to the, well, I need to spread that out a little bit more. Taking the integral now, applying the antiderivative. So I add 1 to 6/5, and 1 in fifths lands is 5/5 plus 6/5 is 11/5. But I have to divide by 11/5, which would be like multiplying by the reciprocal, 5/11. Plus 4 times u to the adding 5/5 to 1/5 would be then 6/5, and we divide by 6/5, which would be like multiplying by 5/6. So I see a little bit of simplifying. Don't forget the plus c. So I'm going to distribute this 1/2 everywhere. I got 5/11. Let's go ahead and throw in u2. What is u? U is e to the 2x minus 4. So 5, not 11. So I'm multiplying by 1/2. So I get 5/22 e to the 2x minus 4, all raised to the 11/5 power. I'm not going to change that to radical because that is kind of ugly. I do have some possible simplifying here with the 4 and the 6. So that would be 2 and 3, and then I'm going to distribute this out, and those 2's are going to cancel. So I will get 5/3. 5/3 u, which is e to the 2x minus 4, all raised to the 6/5 power plus c. There is my answer. All right, hopefully I'm not going too fast, but I'm considering this to be review, so hopefully it's going fast enough for you. All right, so let's move on to the next one. Okay, roll my thing. There we go. All right, so we got to find the integral of x dx over the square root of 16 minus 9x to the 4th. So, and I'm looking at this, right? We talked about it on the past problems where usually we want to make u equal the denominator or the thing in the radical or the radical. So in this case, none of those actually apply here because this is fitting a form. We see something squared here minus something else squared. And we kind of have to have these things kind of in our head. This is where the memorization from Calc 1 comes into play. When we do something like this, and these is a trig inverse. So when we have stuff that can be made to look similar to a trig inverse derivative. Right, so the derivative of sine inverse is 1 over the square root of 1 minus x squared. So the integral of it is this. Let's see. Right. That's one we need to have memorized. Another one we need to have memorized is tangent inverse. So which is 1 over 1 plus x squared dx. The x squared can go in the front or the back. Doesn't matter. So that's tan inverse or arctan. I like arctan better. I just kind of go over this notation to make sure we understand. That is not, right? This is not sine, 1 over sine, right? This is not 1 over tangent. These are the inverse functions. They take, you plug in a ratio and it spits out an angle is what these do, right? Whereas the original function, the original sine function, right? For sine of x equaling whatever y, this is an angle. We plug in an angle, it spits out a ratio. So it does the opposite. All right, so the last one we need is a secant involved. So that is 1 over the absolute value of x times the square root of x squared minus 1 dx, which is equal to secant inverse of x plus c. All right, those are the only three we really need because everything else can be put in terms of it, right? So for cosine, it would just be a negative right there. For tangent, it would just be a negative right there. Cotangent, it would be inverse, it would be a negative right there. For cosecant inverse, we would have a negative right there. So really all we need is these three to kind of do everything we need it to do. Sometimes we might need the other ones just to kind of pull them in, but most of the times we can just focus on these three trig functions, or inverse trig functions, I should say. So looking at this, right, we have a sine thing going on in the bottom, because this can be forced into 1 by factoring out a 16, right? And this is something squared, right? So there we have something squared. All right, so I'm looking at using this, right? It's not this because it has the radical. It is not this because this does not have something in the absolute value outside of it. So we can't force it into either of those. All right, let me erase those. All right, so I'm trying to force this thing into that. So there's a couple ways to do this. What I like to do, and there's kind of some just helpful hints out there in the world to work on that you can use if you don't like this method. But nonetheless, I'm going to force a 1 to be right here, as I kind of talked about before. So how do I do that? So I'm going to have x here still. I don't know what to do with that. Actually, you know what? Let's pull it off to the side so we can hopefully see it. So I want a 1 in the top. So we can have the x over here and the dx over here as well, because I'm going to have to do something with that. But I want a 1 right here. So what I'm going to do is I'm going to factor out a 16. I'm going to divide the denominator really by 16. So, right, we're going to kind of do this. 16, or actually I can just do it up here, 16 and 16. And when we divide it, right, we're pulling it out of the bottom. So this is kind of like getting a square root of 16 in the bottom there. So this is how we do it. All right. So I get that square root of 16. That's going to go right there. I'm going to have under here, I'm going to have 1 minus 9 x to the 4th all over 16. That is something squared. So, and that is 4 on the outside right here. So this is 1/4. So I can bring the 1/4 out of that radical. And let me just rearrange this a little bit more so we can see minus 3x squared all over 4, all squared, all being squared. And then we have the x dx there. That hopefully will go away with something else. So there it is, right? I have something being squared. That something being squared is u. I have a 1 here, which is what I want for the form, 1, 1, and a minus something squared. We have it. This is u. So u equals 3x squared. Let's do it 3/4 x squared. Right? Not squared, but squared. All right. So now we do the derivative. du equals, so 2 times 3/4 x dx. Oh, there's my x. So we had to get rid of it. So now, right, I have the x dx right here. I'm going to replace it, but I don't have this 3/2, so I'm going to move this over. This is how I do this, but there's many ways to do this. 2/3 du equals x dx. Let's replace the x dx now and everything else with u. So I got 1/4. I'm going to take that 2/3 out here. I'm replacing it, right? So x dx is getting replaced by 2/3 du. So there's my 2/3 on the outside. I got 1 over the square root of 1 minus, so that 3x squared over 4 is u and is being squared. Let me put that in red. There we go, and we have x dx, which is that 2/3 du. Put that 2/3 out front. There we go. We got everything in terms of it, and that fits exactly this sine inverse feature. So let's go for it now. So and I can simplify it a little bit here to make this 1/6, 1/6, and we're going to take it. This is the sine inverse of u plus c. And now we plug in u, which is that 3/4 x. So 1/6 sine inverse of 3/4 x, and we can't do anything with that because we don't know what sine inverse does to the 3/4. All right, there's that problem. Hopefully that makes sense, right? Let me pause the video and go on to the next one. Okay, next one, number 6 here, which is find the integral of x plus 3 times x minus 1 all raised to the 25th power. Just the x minus 1 is raised to the 25th power. So I'm looking at this going, all right, I need to do something here. So let's let u be that x minus 1, all right, not to the 25th power, but we're just x minus 1, so that means du is equal to dx. So there is no, right, take the derivative of x, that's dx, and the derivative of -1 is 0. So that's what we have. We can easily replace the dx with du. Oops, let me pause for a second. Okay, so let me go ahead and replace this stuff with what I have so far. But I just got u to the 25th power and du there. I still have this x plus 3, so let me go ahead and figure out how to deal with that. So if I just solve for x, I don't know what that was I just drew on there. If I just take this and solve for x, so add 1 to both sides, u plus 1 equals x. I can sub in x in there, so let's do that. So x is equal to u plus 1. I still have the plus 3 there. And then I have u minus 1 is, I'm sorry, x minus 1 is u, all raised to the 25th power, and dx is du. So I've just replaced everything and made it in terms of u. Let me just simplify a little bit. So that's u to the 25th power. I'm just going to point out this is u plus 4 times u to the 25th power du. I don't have a product rule, but we'll make one kind of this semester. Boom, boom. That can go throughout, right, and make this 26 power, u to the 26th power, and 4u to the 25th power. There is an integral here and a du. Now it's just power rule, so I can do this. So this is u to the 27th divide by 27 plus u 4 u to the 26th divide by 26. I think a 2 can come out of here and here. And plus c. So now let's just finish it up. So u is x minus 1. So we got x minus 1 to the 27th power. Let's write it as 1/27th. It just looks cleaner to me. And 2/13. X minus 1, that's u to the 26th power plus c. There is my integral. I could check it to see if I get back to the original. It will work, but it might take a little manipulation to be able to see that we did get this, that we do get this. Little factoring, yeah, factoring out this bit to see that you got x plus 3 on the rest of it. So, all right, so there's that one. Let's move on to the next one. Okay, so now we got find the exact value of the definite integral, then use Desmos to show that what you just found visually, as well as to check your work. All right, so let's do this, right? So first we're gonna find the exact value of the definite integral. All right, so let's go for it here. Wow. All right, so let's let u, where am I? Here I am. let's let u be everything under the radical. I'm not going to do the full radical. I'm just going to do everything under the radical. I'm just taking a guess here. This is my educated guess. Because I have the radical under the radical, I'm just going to go with this and see what happens. So du is equal to 4 goes away. We got negative 1/2, so that's a half power, right? Times x to the negative 1/2 power dx. And so I don't have the 1/2. I don't have the two. I don't have the x to the, or I don't have. Let's kind of just rearrange this. So this is 2 square root x dx. All right, du. Is equal to this. So I don't have this stuff right here. So let's push it off to the side. I'm gonna just replace du by multiplying by negative 2 square root of x on both sides. I get 2 square root of x du equals dx. So I just multiply by negative 2 square root of x on both sides of this equation. Okay, so that's what we got. All right, so now I can replace that. So I'm just going to take a second and look at this and see what I got here. So forget the limits, the bounds here. So we got 0 and 9 as the bounds. So I'm going to forget those for a second, and I'll come back to it. I want everything in terms of u. So I got this right in terms of u, but now I have this dx thing. So right, I have the square root. Here's the square root of u. This is all u right there, and then I have this dx. I need to replace the dx, and so this has to go in there. So let's see what we have. We have the negative 2 can come out front. That doesn't matter. And then we have times the square root of x, right? Du is du. That is dx, right? I'm just replacing all of this right here, here, and here. So, all right. So notice that this is a horrible u. Don't notice that part, but notice that we still have this x involved and we need to deal with it. But I have, right, I can actually solve this equation for x. So let's do that. Right, I'm going to take a second, come over here, say u equals 4 minus the square root of x. Let's move over there and take a second to solve. I'm going to add the square root of x. I'm going to add and maybe subtract the u at the same time. Subtract u, add the square root of x to both sides. So these kind of go away. These go away. I'll get the positive, right? There's other ways to do this, but this is how I think about it. So I get positive square root of x equals 4 minus u. So now I can replace that. Now I can replace that square root of x because I solved for it. All right, so with 4 minus u, that's a really nice thing. So let's also change u to, we'll make that u to the 1/2 power, and then this square root of x is 4 minus u. Oh, I can distribute this boop, boop, into there. I'll get negative 2 4u to the 1/2 power minus, that's u to the 1 power, which is 2 over 2, plus 1 over 2 is 3 over 2. Du is this whole thing. Let me go ahead and whoop, whoop this in because I don't like it there. I'm just making this as nice as possible. The last thing I want to do here, so this is negative 8u to the 1/2 plus 2u to the 3/2, and we'll see what happens, du. The last thing I want to do is the integrants, so the bounds that we have here. My dog barking again. So these bounds, these are in terms of x. Yes, I could come and do this and then replace it and put them back, but I want to show you a little technique, and I just want to let you know that some of us mathematicians get a little upset by notation here. If you put 0 and 9 up here somewhere, right, it's wrong because we have things in terms of u and it's not right. So we want, if we have things in terms of u, these bounds are in terms of x, we want to change them to be in terms of u. So what do? Is we take this and we say, okay, if x equals 0, then we have u equals 4 minus the square root of 0, which is 4. right? If x equals 9 as our upper bound, we then our u will equal 4 minus the square root of 9. That's 4 minus 3, which is 1. So we have our new bounds in terms of u, right? Now notice this is the lower bound and this is the upper bound. So this is on the bottom, this is on the top, even though those numbers are different, right? Even though it kind of switched them up, and usually we think of the smaller number here and the bigger number up top, right? But if I do that, if I switch them in terms of order, I will get the opposite of what I want. So we want to keep the order of, right, 0, 4 goes with 0, so that will be in the bottom. So 4 goes here, right? 1 goes with 9, so that will be in the top. 1 goes right there. And then we have our integral in terms of all u, and all I have to do, I don't even have to sub x back in, so we can just do it. All right, so let's do it. So so now I'm taking the integral, I get negative 8 u to the 3/2 power. I am going to multiply by the reciprocal of that power, which is 2/3, and then I have plus 2u to the adding 1 to the 3/2 would be 2/2 plus 3/2 is 5/2, and I'm going to multiply by the reciprocal of 2/5. Don't forget we don't need our plus c because we're doing bounds, right? We are going to integrate this, and this is the symbol we use from 4 to 1. The 1 comes first in this case. All right, so is there any more simplifying I can do? Probably I can do negative 16/3 u to the 3/2 plus 4/5 u to the 5/2, and we're going to evaluate this again. All right, so let's go for it now. So let's plug these things in. So first things first, I plug in 1, the top one. So I get negative 16/3 plus 4/5. When I plug in 1, because that u is the 1, and u to the 3/2 is 1, and u to the 5/2 is 1. All right, so now I'm going to do 4. So then I would subtract off negative 16/3, 4, so halving, right? The half power is the square root, so that's 2 to the 3rd power, which is 8. So 4 to the 3/2 power is 8. This is what I'm saying there. Plus 4/5 u to the 5/2 powers, or 4 to the 5/2 powers. I'm going to take the square root first, that's 2, then I'm going to bring it up to the 5th power, which the 5th power of 2 I believe is 32. Did I do that right? Because this is the 3rd power, 4th power would be 16, 5th power would be 32. Okay. All right. So we got it all. Now we just kind of need to simplify and do some fraction work on fractions. All right. It's all fine. We can do this. So what's my denominator? I need to multiply by 5. Oosh, this is ugly. This is ugly. Do I really want to do this? Not really, but this is going to be ugly because I can't really simplify these. So I'm going to use a calculator because I can't do this in my head. And let's go to my favorite calculator of all, particularly my favorite scientific calculator, but my favorite graphing calculator is Desmos as well. All right, so I just want to plug this stuff in there. So I'm going to cheat a little bit and use the fraction work. So let's go negative 16. Let's just put this stuff in there without actually doing it because it is just a lot. Plus 4 divided by 5. So I'm not putting the other stuff in there. I'm just kind of doing it and seeing what Desmos does for me. Minus parentheses negative 16 divided by 3 times 8. So all the purple stuff is what I'm putting in. Plus 4 divided by 5. I'm going to scoot over times 32. And then I'm going to end that parentheses. It comes up with this decimal number. I hate decimals, but especially because this one goes on forever. So we can't work with that. Well, let's get a fraction instead. And Desmos is just too good to do it for us. So there's a bunch of fraction where it's shortened up into an ugly answer of 118 over 15. That's the exact value. That is what we want, but we could approximate it as an answer to 12.5 5, 3. I don't know why approximate. Let's just put a little bar over there just to make sure people know it just goes on forever, right? Why actually approximate? We do not like approximating in mathematics because we don't know if we're talking about going into space or just rebuilding a road, right? Very different outcomes on whether we're talking about light years, 12 light years versus 12 inches, right? So, and how we're going to report that out. All right. So that is that problem, except I did want to finish it up with what it told me to finish up with, which is find the exact value of the definite integral, then use Desmos to show what you just found visually, as well as to check your work. All right, so let's go for it. So I'm going to go to my other favorite calculator, the graphing calculator of Desmos. So those of you who don't know me, I love this stuff. And those of you who do know me probably took it because I love this stuff. So let me flip my computer around a bit so I can type things on it. Oops. All right, so our integral is of this function. So let's look at what this function looks like. Equals the square root of 4 minus the square root of x. And there it goes. This is what this function looks like. Oh, look at that. It just stops over here. So it's in between 0 and something like 16. Yeah, it stops at 16 because then we get a, right, anything above 16, we would get a negative underneath this outside radical. Anything below 0, I don't know. Oh, wait, you can't plug anything below 0 because that's negative there, and we get that undefined feature there, or complex numbers, and we don't go over complex numbers calculus. That's for a complex number class. All right, so I have this function. I want to do something with it, right? So I'm going to talk about what we just found. We're going from 0 to 9, right? So let's restrict our x's from 0. So I use the squiggly brackets for the set notation. So and I do less than or equal to x, less than or equal to. So I hit less than symbol and the equals to symbol, and then I finish it off, and that truncated it in between there. I can actually take this function if I want the full thing graphed out, Control C, Control V, but I need those boundaries. So so this helps me graph out the whole thing so I can just see it, but this makes it so it's bounded in between 0 and 9, those limits, okay? So you can even do A and B. Yeah, some of my students last semester made this A and this B kind of like what we call it in the integral. And then you can add slider, and you can make this 9 and this 0 to force it to be that way, all right? So, and then you can even slide it, which might be a cool thing to kind of show here. So I'll do that in a second, but nonetheless, I want to finish this up. What we are showing here is we are talking about the area under the curve bounded from x equaling 0 to x equaling 9. So let me do A and B. So we are bounded between these two areas, and then our y value is in between the f of x and the 0. So we go, and f of x is always above, so I don't have to worry about the other case. So 0 is less than or equal to, y is less than or equal to, this is the big shading part to show you what we're shading, f of x. And there it is, right? And so this is the cool part. When we put sliders in here, we can increase the sliders and decrease the sliders. You can change the bounds so it's right to 16 like we want to, and 0. So enter, and then we can increase all the way and decrease, right? We can even increase this, and oh no, we can't decrease that, but we can increase there to kind of really look at what we're doing. But we're really just looking from 0 to 9. So let's change this from 0 to 9. This is the area we just found as this, what did I find it to be? 12.5 or 188 over 15. Let's go ahead and look at it and check it another way, because Desmos also understands definite integrals. So little bit of cheating here, but I love checking the work, and I will ask you to check your work to make sure that you understand how to do this. There it is, right? So you can even change it to a fraction to get that exact value. So so I don't think it does radicals, but I don't know. I haven't really tried it on those, but this kind of button just came up last semester. So here we are. We have a way to check to make sure our answer is correct. We also have a way to visualize what we just found out. This area, this blue area right here, is what we just found exactly as 188 over 15. And it's kind of mind-blowing to me how cool that is, and the exact value of this area under the curve. All right, so let's pause there and we'll go on to the next one. All right, so another one. Find the exact value of the definite integral, then use Desmos to show what you just found visually as well as to check your work, right? So the check your work was using the integral, that showing visually was graphing it out at least and saying what the area is. All right, so that's what we have here. So we have this integral from pi over 6 to 2 pi over 3 of x to the third power minus 2 cosecant of x times cotangent of x dx. All right, so let's look at this. Oh wait, this is just a power rule. This is just the integral of that is just cotangent of x, right? Negative cotangent. So it is negative. So that'll come around. All right, so I don't need to change. I don't need to u-Substitution. This is just a simple direct relationship. So we'll have x to the fourth divide by 4 multiply by 1/4. There we go. Minus 2. So the minus will go away and it'll become plus because the derivative of cotangent is negative cosecant cotangent, and so that is positive cotangent. So that negative is going into the integral that we have. And there's a plus c, but we are going to evaluate this from pi over 6 to 2 pi over 3. I'm sorry, I did this wrong. I said cotangent. The derivative of cotangent is negative cosecant squared. The derivative of cosecant is negative cosecant cotangent. I apologize. So this is positive cosecant is the derivative of this. The 2 just comes along for the right. All right, now we can plug this thing in that I have it right. I think. You have to check me. I'm trying to do my best on these videos so I don't have to do them again. But nonetheless, you always have to check and make sure you understand why those things are what they are. And that's what I was doing in my head as I said this. And this ugly thing is a 4. All right, so let's plug these things in there. So you got 1/4. We're going to plug in 2 pi over 3 first. So you got 2 pi over 3 all to the 4th power plus 2 cosecant of 2 pi over 3 minus 1/4 of, now we're going to plug in the bottom bound, pi over 6 to the 4th power plus 2 cosecant of 2 pi over 3. I'm sorry, not 2 pi over 3, pi over 6. I'm plugging in the second line. Pi over 6. So let's do a little mathematical manipulation if we can here, so to make this happen for us. So we got 2 raised to the 4th power is 16 pi over 4 times 3 raised to the 4th power is 81. Seeing some canceling, that'll be 4, right? That'll be 1. All right, so now next I got plus 2 times cosecant of 2 pi over 3. So now I have to think unit circle wise, where is that? 2 pi over 3 is up here. Oh, that was ugly. More like this. I'm separating pi 180 degree into 3s. So this is 120 degrees if you're into the degrees. So, and my cosecant refers to the y value as the reciprocal of the y value here, which is the bigger of the two numbers on that point, is how I do this, and which is root 3 over 2. The y value of that point is root 3 over 2. The cosecant of that is the reciprocal, so 2 over root 3. All right, minus, let's do this. What is 2 to the 4th power? Let's go to Desmos, tab, there it is. Desmos Scientific Calculator. This is my previous one. 6 to the 4th power is 1296. So we got 1 pi to the 4th. Did I do pi to the 4th over here? I did not. That would have been a problem. Pi to the 4th over that number times 4. Let's times it by 4. Times by 4. All right, so 5,184. 5,184 plus 2 times the cosecant of pi over 6. Where is pi over 6 on the unit circle? That's the 30-degree mark here. Again, cosecant talks about the y value at that point. The y value is the smaller number, which is 1/2. And if we flip 1/2, because cosecant is the reciprocal of it, we get 2. So, so this is just 2 times 2. 2, yeah. All right, so let's just simplify it a little bit. Pi to the 4th power over 8. Oh, I forgot the 4 there. Plus 4 over root 3. I can rationalize that, yes, but it's ugly. Pi to the 4th over 5,184 plus 4. All of that, whatever that is, I want to just see what the heck Desmos gives me. Does it just like, bah, or does it give me something a little bit more simplified? Let's go ahead and plug it into Desmos Scientific just to see. Pi gets you pi, or you can use the function stuff down below. 4 to the power of 4, all divided by 81. Scooch over, plus I have some of you in my class that are really fast users of Desmos, and I'm intrigued about how well you'll do this semester with it, because we can get into some really cool stuff here, like rotations and 3-dimensional objects and stuff like that. So pi to the 4th, I did not distribute this negative over either, so that was a problem. This should be negative, and so should this. Or I can put it in parentheses to make sure I got it right. So pi to the 4th divided by 5,184, which is right above, and minus 4. There we go. That's what that is. It doesn't give me an option to flip it to a fraction as it does there, so it really can't simplify that too much. So that is the approximation. This is basically the exact value. I would not make you simplify this anymore, because you'd have to rationalize this for 1, then you'd have to find a common denominator, and it's just ugly. So this is the exact value of this. Let me box it a little better, and then maybe you can throw a little approximation symbol here, but we always like exact values. 3.101, I don't know, something like that is approximately what it is. All right, or you can write down that whole thing just to make sure you know what it is. We did want to use Desmos on this piece to see if we get the same thing, to see if we understand what we're doing here, so let's go for it. So I want you to explain to me how to do it, and this is a way to do that if you want to. So you can just change this function to what we have here. So we got 1 divided by 4, x to the 4th power, x to the 3rd power, sorry, I'm putting the original function in, minus cosecant, 2 cosecant of x times cotangent of x. So it's having problems. So if we come over here, use parentheses around cosecant. So it wants to know what you're taking the cosecant of, which is this. It wants to know what you're taking the cosecant of, which is this. All right. All right, so I'm just trying to show you what I have here. I have the squiggly brackets AB. I can choose AB to be what I want them to be, pun intended. So A is, right, this pi over 6, so pi divided by 6. B is 2 pi, 2 pi divided by 3. There is the little region I'm looking at here. I don't want this formula. What I can do is graph this out. My dog's gonna have a lot of things delivered. Let me pause for a second. Okay, so where was I? I think I was copying this over Control C and then down to here because I got this weird, this is the other one, you got to copy that. Fine. If you want the full graph to see the full graph of this thing, which is kind of funky and weird. So let's just look at this piece here now. And I have, this didn't change automatically. And the reason why is because I did not put an A and a B here to make that work for myself. So now I have it. So this gives me exactly that value. This does it for me unless I get a negative version of it. So this is A and B. So I am bounded. I do have a negative version, see, so it's right there. So let's go and get that portion too. So I need an extra bit for that negative. So f of x is less than or equal to y is less than or equal to 0. And that gets you the negative version. So, all right, so this is what we have. I'm gonna do a little stretching here of this x-axis. So I'm gonna go from -1 to, let's go to 4. Stretch it out a bit, and that's fine for the y-axis. And now we can see this negative region added to this positive region, and the answer is not what I got. Wait a minute, 2 pi. Let's make sure I got this. That is not what we got over here. So it's telling me the integral from pi over 6 to 2 pi over 3 is negative 0.4927 blah blah blah, right? It cannot do the fraction again, I don't think, but I can't see it because it zooms in the way. Did I enter everything right? So first things first, let's make sure I entered everything right. So I'm going to take a second and look at this and try and come back and try and find my issue, and then come back into this lesson and try and make sure you understand what I found. And sometimes watching me do this can help figure out, so let me just go through this. If you want to fast forward to the end of this and get to that answer. So let's see. So I determined it was 3.3, but this is saying the integral is this. Did I enter it in right? I did not. Why do I have a quarter there? I don't know. All right, so that is a big portion. I got the same thing now. That's it. It's just a simple mistake. Glad I didn't pause. All right, so let me readjust this. All right, axis. So my y-axis isn't tall enough. Let me stretch out and go from -1 to 3. Stretch this thing out. There we go. All right. What did I have here? Okay, it's because I have a quarter here in this wrong function. All right, so now I see my function is matching up. I'm drawing out the full function so you can kind of see how funky function this is, right? This is a funky function, and it's awesome. All right, but we are just concerned about this one region from this pi over 6, which is right here. By the way, you can change your steps here to be in terms of pi, I think, like, maybe I'll try 6. Yes, okay, it does do 6. It used to not be able to do this. But it used to be able to do pi's. It just wasn't able to bring it down to like pi over 6. There it is. So, but now it is. So that's great. So you can see the pi over 6, from pi over 6 to 2 pi over 3, right? There is a switch. So this is a negative region. This is a positive region. Clearly the positive region is bigger. So we're getting a positive result. So as this is being subtracted off from that region. All right. So, and that is what we're looking at. That is what we just found. The addition of these two regions. Again, this is positive. This is negative. All right. Cool. So let's go ahead and pause the video and get the next one going. Okay, so number 9 here, I think we only got 3 more or so. So if v of t equals 3t squared minus 19t minus 14 represents the velocity function in centimeters per second of an object during the time period from 0 to 10, find the following, and these are seconds, right, because it's giving me the units here. Find the following: the displacement of the object over the given time period, the total distance traveled by the object, right? So I'm just making sure we understand it's a time period, not just a period or something. So, so you understand this is an element of time. So that's why it's underlined. It's trying to correct me, but I want to make sure you understand that, what we're talking about there. T is a time, right? And we're plugging into the velocity function and it spits out the velocity in centimeters per second. So with this function, right, we can find the total displacement of the object. And as talked about within the program, right, total displacement. So if I have a particle that starts here, goes forward, then goes back to here, right, the total displacement is this distance. Displacement, whereas the total distance we have to take, right, this distance plus this distance, d1 plus d2, total distance equals d1 plus d2. So we have to add those two areas together, or really because d1 will be negative, the distance. Well, so the problem with d1 is if we just integrate, we will get some negative stuff. And I don't know exactly what happens with this. We could kind of talk about it with the graph, and maybe I can show it with the graph later on. But it might change from being positive to negative at some point. So, and I have to worry about that, particularly for the total distance. The displacement is easy. Displacement, on the other hand, is just, oh, let's take the integral from 0 to 10. And then we find the displacement. So the integral from 0 to 10 of this thing will get me the displacement. Displacement equals 0 to 10 of 3t squared minus 19t, that's a 2, 19t minus 14 dt is what we're taking over there. So this is an easy integral. So let's go for it. We're going to do 3t cubed over 3. Nice. Those are going to divide. Bam, bam. Minus 19t squared over 2 minus 14t. And we're going to go from 0 to 10. All right. It's really easy to plug these in. So that is 10 to the third power is 10 times 10 times 10, or 1,000, minus 19 times 100 divided by 2. Divided by 2 is then 950. 1900 divided by 2 is 950. Yeah. Make sure in my head, I'm doing it in my head, it's never safe bet, and this 10 times this is that, and then if I plug in 0, I'm minusing 0. So we just have this really. So total displacement, I'm looking maybe negative here, right? So that's 50 is left. I have minusing 40, that's negative 90, it looks like. So is the total displacement. So meaning that really, right, we did something like this. Maybe we went forward then backwards, or maybe we went backwards then forwards, and we are now here, back 90 something centimeters, right, is where we are. So this is 90 centimeters, by the way. I forgot my units, and units are super important in this class. super duper important. We want to be able to think about the units, and what I love about calculus is that the units work with derivatives and integrals. All right. So there's the displacement. Now we need the total distance. So now we need to include this back part and where it goes, where it stops here, and then this front part. But the problem is we need to find the time when this turnaround happens, right? So that way we can say, oh, the total distance would be the addition of this D1 and this D2. But right, those distances, because they are a distance, is always positive, kind of thing. Right? When we talk about displacement, it's about a positional spot. So the position is that we're negative 90 centimeters back from where we started, wherever back is. Right. So, and I just use the number line backwards to kind of get us there. All right. So now we're going to do total displacement, but I really need to find this time when it is here. So the question I have for you is, what is the velocity when we hit that spot? The velocity is negative here because we're going backwards, negative, negative, negative. And I believe it's negative in this whole region. And then all of a sudden it turns positive. What is the only number that is not negative and not positive? So that would be 0. And our velocity has to reach that because this is a continuous differentiable function everywhere. So it is a beautiful function. It's a polynomial, right? So where is v of t equaling 0? That'll get us that spot, the time. This is the time we are looking for. We're looking for t here. So v of t equals 0. So v of t is 3t squared minus 19t minus 14 equals 0. Oh, that is the ugliest thing I've ever seen. I want to factor it. My go-to method is factoring, right? But can I factor it like that? Woo! I don't know. I can use diamond method to do this. So 3 times 14 would be 30, 42, negative 42. Oh, great. Sorry. All right. Negative 42, and we're trying to find two numbers that add up to negative 42, yet add up to this. Let me do this. I'm going to power off my phone because people are texting me like crazy and it's not important. All right. So negative 42 over 19. So I want two numbers that multiply up to 42, negative 42, and add up to negative 19, or really subtract because they're going to be difference. So let me see. So I know it's not going to be, sometimes I just exhaust the method. 1 times 42 is definitely not going to be it. 2 times, what would that be, 21? Oh, look at that. The difference of those two is 19. So if I make 21 be negative and 2 be positive, then I can get that addition. So what we do now is we separate it. So if you haven't seen this factoring style, right, no big deal. Reuse quadratic equation, it'll get the same things. And then, but you can do it this way too if you understand it. So 3t squared minus 21t minus plus 2t minus 14 equals 0. It's called factoring by grouping now. So I'm grouping these together. These two are the same, right? It gets me those two things. Let me pause for a second. No, I'm okay. It's just stuff going on. All right. So I'm going to group these together and factor out everything I can, which is 3t times, what do I get left? I get a t minus 7. So if I did this right, I'll factor out everything I can from the next grouping, these two, which is 2. I should get the same thing, t minus 7 equals 0. That means I can factor out the t minus 7. I'll get 3t plus 2 times t minus 7 equals 0. So now I can solve it, either 3t plus 2 equals 0, or t minus 7 equals 0. There's my dog again. Everything's happening today. The first video I make for this class. There we go, plus 7. And then I'm going to subtract 2. 3t equals negative 2. Divide by 3. I get negative 2/3 there. All right, so and here t equals 7. So if I look at these, I think, oh my gosh, I have 2 places. Oh no, what do I do? Well, so for one thing, we can look at the original problem and see that we're looking from 0 to 10. We can also think this is time, right? Unless you're Marty McFly, you can't do this. All right, and yes, that was a joke, right? Watch Back to the Future if you haven't already, because it's an amazing movie. All right, so t equals 7 is the number we're looking at. That is where that turn happens. So we need to divvy up our integral into the pieces. So we got 3t squared minus 19t minus 14, and we're going to divvy it up into the pieces to be able to help us. We're going to go from 0 to 7 of this 3t squared minus 19t minus 14 dt. And we are going to take that and we are going to add it to the integral of from 7 to 10 is where we last wanted to do. So that's kind of like the positive thing. This one's going to be negative, this one's going to be positive, but we want to add the positive results of both, right? So how do I deal with that? Whether one's positive or negative, we can deal with it this way. But we have to find that that value first that separates those positive and negative values. So the program kind of talks about, well, you just do this. You just do an integral from 0 to 10 of the absolute value of 3t squared minus 19t minus 14. That doesn't explain it, because this doesn't mean anything to me, because we want it all to be positive. All of the regions to be positive, yes, but I don't know how to deal with that mathematically. This is how we deal with it mathematically. If we get a negative result from this integral, we will make it positive with the absolute value. If we get a negative result from this integral, we will make it positive here, and we will add those two things together because distance is positive. All right, so that's how I do it. Let's go ahead and do this here. So we already did the integral, so that's done, right? T cubed minus 19 halves t squared minus 14t. So t cubed minus 19 halves t squared minus 14t. We're going to evaluate this from 0 to 7 first, and we'll take the absolute value of it. So let's go for it. So if I plug in 7, right, so that's 7 cubed, I have no clue what that is, minus 19 over 2 times 49, 7 squared, minus 14 times 7, I don't know. I could probably figure it out, but I'm not going to. Let's go ahead and use Desmos to figure out what this is. Where's Desmos? There it is. I don't want to do that Desmos. I want this Desmos. Enter. So we got 7 cubed, scooch over, minus 19 times 49 divided by 2. Oops, I forgot to put minus right here. Minus 14 times 7. That gets me that, which is just a fraction, but it's also easy enough to write as a terminating decimal, so it's easy enough to write as a decimal too. So that's the negative version, right? I want the positive version, so I need to do the absolute value of this stuff, right? Everywhere. I can't even do this absolute value over there, and then that would just be the positive version. So we're just making it positive because that's how far we've gone. We want that distance is 220.5, I think they're centimeters we're talking about here. So let's do the next one, right? So next one. So we're going to do the integral from, oops, I want purple, the integral from 0, not 0, but 7 to 10 of 3 t squared minus 19t minus 14 dt. Right, and we can do the absolute value of this, but we don't have to because we know it's going to be positive. I know this because we have a parabola here, and the shape of a parabola, one side would be negative, the other side would be positive. All right, so let's go for it and see what we get. And then maybe I'll graph it just to show you, but I didn't ask you to do that here. I just wanted you to find it. All right, so we already found 7 when we plug it in. We just did it. It's the negative 220.5. Can't say numbers today. All right, so so when we do this, we can kind of use those results. We even found the 10. When we plug in the 10, we did that up here. What did we get? When we plugged in 10, we got negative 90, right? So plug in 10, I get negative 90. I plug in 7, we are subtracting off the negative 220.5. And so we are going to take negative 90 plus 220.5. And then we get 130.5. There it is. All right, so this is centimeters, right, of total distance we've traveled. So those are the answers, right? We had negative 90 as the displacement and negative 90 as this displacement and 130. Let me go to Desmos to take a second and help you understand what we just found out a little bit better by doing this. So let's go ahead and replace these. I need to flip my computer around. So I'll replace it with my 3t, well, not t's, let's use x's to not confuse it. 3x squared minus 19x minus 14 is the function. All right, so and then I want to reduplicate this right here because it's confusing. All right, so and then we're going from, let's make this bottom one 0 to 10, and then that helps us see we get negative 90 as the total displacement. So what's happening here, so if we look at our velocity, right, this is our velocity function. Right at 0, we already have a negative velocity, so something like negative 14, yeah. Negative 14 is our velocity, so we're going backwards already. So we keep going backwards and keep going backwards. When our velocity hits 0, which is right here, right? So it's actually our velocity is decreasing, right? Meaning that it's getting more and more negative, right? Faster and faster, up to negative 44 centimeters per second at the highest peak of it, right? But then the velocity is 0, so the y value is the velocity. When the velocity is 0, that's where our velocity changes from negative to positive, and we have a positive region here. So we have a positive region here. Then we have this positive region, so our velocity is positive. But notice this area is kind of smaller than this purple area, so this positive region doesn't make it back in time. In fact, right, this area is right 90 centimeters different than this area. So, so we get that negative 90 result of the displacement. But when we add these two, right, so this area is that, I don't think we found this. Oh no, this is the 7. So this is the 220.5, the negative 220.5 that we found right here. And this area is the 90 that we found. No, that area, sorry, I'm having problems with this. Total is negative 90. This area, did we not find this area? Subtract and we get a difference of that. Did I not? I'm confusing myself because I think my work over here is a little confusing. This was 130. I did not answer the question. This was 130.5, but now we need to take these two areas together. So sorry. So I was confusing myself because I did not finish this technically. I just realized. So it was a good thing I kind of came over here and was talking about it, because this 130.5 is actually the blue area that we have here. This 220.5 is from 0, is the integral from 0 to 7, so that's this purple area. So if we add these two areas together, we get the total distance. Total is equal to 130.5 plus 220.5, which adding them would get us 350 centimeters, 51 centimeters. So that total is, yeah, 351 centimeters. There we go. All right, so so you can check it kind of by looking at this stuff. You got the negative 90. If I changed B, I guess to 7. So if I changed B to 7, I would hopefully get that to 220.5. It's negative. So if I change this one to 7 and then this to 10, I should get that 130.5 region, that blue region. That helps me say, okay, now I can add them up, that 130.5 and the 220 to get the total distance traveled. All right, cool. I'm really glad I went through that motions, because I wouldn't have caught my error. So hopefully you were able to watch that all the way through to kind of see that my answer was different in the end, with the 351 as the total distance traveled, as opposed to what I was saying it was, which was that, right? So, all right. Let me pause and go on to the next one. I think I got 2 more. Oh, that didn't work. Pause. Okay, so find the area bounded by the given curves. Use Desmos to explain the typical rectangle and how you came up with your integral, as well as to explain the area you are finding. So I'm going to do this by hand at first, and then I'll use Desmos. Many of you might just kind of jump into Desmos here because we are trying to graph it. I want to just say, right, there are steps here that can kind of help you do this without the graphing tool. So, right, if you're thinking of an exam or something like that, you need to do this on exam. You don't have the graphing tool there. There are ways to do this, so I want to kind of set that up so you understand how to do it on that. I forgot to flip my computer around so I can write on it. Okay, now that I have that, let's go for it here. All right, so what I want to do is I want to find the area bounded. And so if I look at these, right, I can think about, hopefully in general, what the graph of these would look like. And that really does help me kind of think about what I got. So, right, so this first one, for instance, let me use different colors for this. I don't need to be neat about it, and so I'm going to make it small. So it's 12 minus x squared. So that's a negative x squared kind of thing. So it's a downward facing parabola, and it's starting at 12. So up here is going to hit 12 right there. Do it. There it goes. That's supposed to be a 12. So, and it's a downward facing parabola. That's all I really care about, right? It doesn't have to be perfect. This one, on the other hand, is an upward facing parabola at -6, starts at -6, and it goes upward. So this is -6, but the -6 don't matter, right? And neither does the 12. It's just that these are downward facing parabolas. We are finding the area bounded by this. So we are talking about this area right here from here. And we need to find the x value here and the x value here of those two intersection points. How do we determine the x values of an intersection point? Is we set the equations equal to each other, because there's y, there's y. At these particular points, our y's are equal. right, to each other. So we set it equal to each other. They are equal in general, right? It's supposed to be flat, but that's my horrible drawing. But if we set them equal to each other, we will find the x values that get it to us, and we should find 2. Let's see. So I'm going to solve this thing. Let's get all our x's on one side and all our numbers on the others. This is a quadratic, but it looks like I can get x squared by itself. So I can just use the square root property to do it. So I'm going to add 6. I'm going to add x squared to get this x squared to cancel. I'm going to add 6 on both sides to get this 6 to cancel. Now something's happening. Sorry. There we go. So what do I get? I get 18 on this side equals 2x squared. If I divide by 2, I get, I'm going to flip-flop the x squared. I get x squared equals 9. If I square root it, right, now I'm going to square root it, but what do I need to remember when I square root things? I get the plus or minus feature. X equals plus or minus square root of 9, which is plus or minus 3. Excellent. Those are excellent numbers to use. Now we can do it. We can do the integral from -3 to 3, or knowing symmetry is going to happen here, we can do it from 0 to 3, and then times it by 2 to get that going on. So let's just do from the integral from I meant to put 3 there, and I put 0 there. All right, you know what? You do from -3 to 3, and I'll do from 0 to 3, and I want to multiply by 2 using symmetry idea that I just talked about. I know these are symmetric. These are symmetric about the y-axis, both of these, and so our area, this area will be the same as this area. So I'm going to use some area techniques to kind of help you see some things. And you do it from -3 to 3, and let's see if we get the same thing. All right. So the other thing I need to do is I asked you to do the typical rectangle. So let me get rid of some things here and kind of talk about that. I'll do in Desmos as well to kind of show you. But what we're trying to do is just kind of make sure we understand what we are subtracting from what. So let me do it in a different color. Let's use blue, right? So if I have this to this, let's say that's my straight up rectangle. They say to use the leftmost point. It doesn't really matter, just as long as you know here is a typical rectangle that we are thinking about this rectangle, and we are going to make this rectangle infinitesimally small, meaning the width here is dx, because the width is parallel to the x-axis, and the height here is from this function to this function. So if we take this function and we subtract off the green function, we will get the height of our rectangle. So, so I'm going to use red. So here is the red function on top, and I am going to subtract off the green function, which is x squared. Ooh, why did I go blue? I don't know. X squared minus 6. Let's make sure I throw some parentheses around these things. So, and then our width, right? So this is just our height that we just determined. So this is our height of our rectangle. I before E, except after C. That doesn't work here. Height, E before, yeah. Height. It always confuses me. And then our little width there that we need to multiply by is dx. So let's not forget the dx. Right? And this really does help us. This notation helps us understand, oh, there's a little width. And our height is this minus this. And we're going to do this in multiple places this semester. So getting down a visualization really does help us to understand, okay, it's this one minus this one, and I'm multiplying by the width. And I know it's a dx. And we're going to switch that on you and make it a dy in some cases. And so we need to know whether it's a dx or a dy. And that's how we know. We know the infinitesimally small width is parallel to the x-axis, so it is dx. If the infinitesimally small width is parallel to the y-axis, then we would use dy. All right, so now we can just do this. So let's go for it. So we're going to do the integral. Let me simplify it a little bit, 0 to 3, right? So I got, distribute that, that becomes plus, this is 18 minus 2x squared, that looks familiar, dx, much easier to take the integral of. 18x minus 2x cubed divided by 3, and we're going to evaluate from 0 to 3, and let's not forget our 2. So maybe I distribute this 2 throughout, because that's just kind of how, if I have numbers there anyways, I might as well just make them the same. So this is 36, and this 2 becomes 4. Make this easier on me. Go 4. All right. There's that. I did the integral. Now I need to apply it. Now remember that 2 came from, I am doing the integral from 0 to 3, and I multiply by 2 to get both pieces. I'll show the symmetry better in Desmos after this. So, all right, so we did that. Let's plug in our values. This is 36 times 3 minus 4 times 3 cubed is 27. That's a times over 3. And then we are subtracting 0, because when I plug in 0, I get 0. So I just need to figure out what this is. So let's go to Desmos and do that piece. Where was it? So 36 times 3 minus 4. I'm just going to do 4 times 9. 72, right? Because I just canceled out this 3 with this 27 to get 9. All right, so that is 72 is the answer here. 72 is the area of the region bounded by these two curves. So let's see in Desmos what we got. So now I need 2 curves though, all right? So I didn't ask you to do this, but I'm just doing it so that way we can make sure we get the gist of it. So f of x, let's do f of x. Let me, so I can type. 12 minus x squared. You know what, I'm gonna just do blank. There we go. Desmos does like function notation. Sometimes you have to use function notation to do some of the things that we want to do. So there's the first function. Here's my g of x equals x squared minus 6. All right, so there's our 2 functions kind of graphed together. Right, and we are looking for the area bounded between the 2. So if I want to do that, I know my f of x is on top and my g of x is on the bottom. So I would do g of x is less than or equal to y. So generic y is less than or equal to f of x. And we can graph that region. That's the region we just found, the area we just found. So, and now I can do the integral just to check it. I can do my integral from -3 to 3 of, we want f of x on the top. I need some parentheses around here to make sure it's all in the integral. And notice it's not coming up with anything because you need a dx. Otherwise it doesn't do it. So it did. Right? So there is my integral, my answer 72. That's what I got, and it is that area under the curve. Again, a typical column if I want to graph it. Let me Epic Pen. Epic Pen isn't open. just allows me to graph on here. So we can think of graphing right here. I'm going to draw a little rectangle going straight up a little bit, right? So this is what we're talking about, right? Making up infinitely many of these rectangles. My width is my change in my x, right, which will make infinitesimally small, so we can call it dx as opposed to delta x. My height is, right, this function f of x minus g of x will get that value. So this height, overall total height, is f of x minus g of x. So hopefully that helps you make sense of this. Understand this a little bit more. I have one more and then we're done for the day. All right, so let me pause again. How do I pause? There we go. Nope. All right. So let's find the area bounded by the given curves. Use Desmos to explain the typical rectangle and how you came up with your integral, as well as to explain the area you are finding. So here are the two regions. So let's think about these for a second. And again, I'll kind of graph it out briefly, right, in an easy way to kind of think about, okay, what does this look like? What bounded region am I talking about here? So let's go for that first and express that. So again, I'm just going to make up an ugly graph, right? I just need to know what these look like. This one is a sideways parabola with, if I plug in 1, I get 0, right? So if I plug in x equaling 1, so it's going to start at 1, and it's going to go like this, is what that graph's going to look like. Let's do red for this one. So this one is a line. So we could solve the line, I guess, by making it y equals, what would it be, x minus 1. So, so at -1, crosses at -1, and it goes up by 1 and over 1. I think they cross right there. And then somewhere later it's going to cross, and I think we're talking about this region. I need to find this point, though. I think this is a point that they share, though. I guess I can test that out, because I said this was at, if I plug in 1, I get 0. So is that true for both of them? If I plug in 1, I get 0 here. If I plug in 1, I get 0 there. So yeah, so they both share that particular point. That is a point. I need to find this other point. Hopefully it's nice too. How do I find that other point? By setting them equal to each other, the y's, and plugging them in. Or you can plug in the x value, and all right, so this is a y value. You can plug it in here and go for it. I have these two equations now, so I'm just gonna set them equal to each other and solve for x. X minus 1 equals the square root of x minus 1. That's interesting. So now we're squaring both sides. I need to get rid of that square root. I don't know how to solve it otherwise. I'm going to FOIL this out. That's x squared minus 2x plus 1 equals x minus 1. Now I need to, it's quadratic, so I need to get everything on one side. So I'm going to subtract x from both sides. I'm going to add 1 to both sides. Add 1. I did it in my head and got 2. There we go. So we got x squared minus 3x plus 2 equals 0. So, right, each quadratic equation needs to be equal to 0 to solve it. Hopefully I can factor this. I think that is x minus 2, x minus 1 equals 0. I think that gets it for us. Yeah, right, yes. All right. So, so x either equals 2 or x equals 1 will get us that 0, right? If I plug in 2, I get 0. If I plug in 1, I get 0, and that's what it is. So we have those two solutions. We already got the 1. We need the other one, but we have it here. So this is 2. This happens at x equaling 2. My graph doesn't show it. So this region that we have bounded, right, with these two functions is going to go from 1 to 2 of these two functions. What is the upper function? It is the square root. What is the lower function? It is the line right here. So, and notice at this point we need the function notation, so we need the y equals 2 so we can subtract these functions. So we're going to take the square root first, So square root of x minus 1, and we're going to subtract off the line minus, notice the parentheses, dx, and we're going to have big parentheses here. So now we can do this integral. Let me go ahead and distribute the negative, make it a little easier, and now we can do the integral. So the integral of, so that is a 1/2 power. So again, we're going to add, it's just a power rule, but there's a little chain in there, but the derivative of the chain is the same as the none. So it's just 1. So we really can ignore the x minus 1 underneath. So we'll get x minus 1, because there is no chain. We have to multiply by nothing there, or 1, I should say. To the 1/2 power, we are going to raise that up by 1 to make it 3/2 power, and we'll divide by 3/2 power or multiply by the reciprocal, which is 2/3. And then we get minus x squared divided by 2 plus x. And we're going to plug in 2 first and go to 1. So let's do that. So I'm going to plug in 2/3. You get 2 minus 1, which is 1 to the 3/2 power, which is just 1. Nice. So we get 2/3 times 1 minus 2 squared is 4, divided by 2 is 2, plus 2. All right. And then we're going to subtract off when we plug in 1. So if I plug in 1 for the first thing, I will get 1 minus 1, which is 0, times 2/3, which is 0. So then I get 1 squared is 1, over 2 is 1/2, plus 1. All right. So now I just need to simplify a little bit. So let's see, we got 2/3, these go away, minus 1 3/2. That's interesting. Now I just need to simplify 2, that's, and then 3, that's 4/6 minus 9/6 equals negative 5/6 as the region bounded by it. All right, I'm pausing. You can probably see that as like, why is he paused? Why isn't he like excited about his answer? Gotta pause. Sorry, take a drink. All right, so there's something wrong here. This is negative, and it shouldn't be negative. As long as I set it up right. So the only reason we would get a negative value is if I inverted, right, what should be if my column isn't the right way. Going from 1 to 2, 1 to 2, 1 to 2, and subtract them off in the right order. You get 0. Let me just check my plugging in. I don't know. 3/2 and 2. I'm not seeing it off the top of my head. So let's go to Desmos to try and figure out what's going on here. I'm going to use the original things in Desmos too. So let's, let me get a blank, new blank. So I'm going to do f of x, because again, it understands function notation. Square root, sqrt of x. I said I was going to use the original ones, and now I'm using function notation, so I can't. G of x is equal to, subtract that, get negative 1 minus x, and then we negate it, get x minus 1. It should be x minus 1. I can check, so I can put in the function to make sure that that line is the same as what I have there. Just to make sure we got x minus y, x minus y. So this, whatever I put here should match that blue line Yes, it does. All right, so that doesn't matter. I just wanted to make sure that I got it right, which I thought I did. So now, right, we are looking at finding this region from 1 to 2. So let's do our shading, just to kind of get a little graph going. My g of x is the smaller one, so g of x is less than or equal to y. I just like seeing this stuff personally, so I don't think I need it here in this case to figure out what's wrong. I don't think it helps me, but it just kind of helps me visualize it. There's my column, right? Let's go ahead and get the column going on. So I can clear, delete, and let's draw the column. So the little column is like this, from here to here. We draw a little rectangle, right? There's my dx, and that's my f of x minus g of x in this case, depending upon what we have. So we're doing f of x minus g of x. So this kind of helps me see if I have any issues with it. So f of x is the square root function, g of x is this. I'm going from 1 to 2, yes. And now let's do the integral. Integral from 1 to 2, let's see if I get the same thing, 1 to 2 of, I'm gonna do parentheses f of x minus g of x dx. And I can change it to a fraction to get 1/6. That is not what I just got. So let me go through this. We're going to do integral from 1 to 2. I'm going to check make sure I got the right thing up there. This QRT of x minus 1 minus x plus 1 dx is that 1/6. So something's off in my work here, because this is right. This is 1/2 power. Bring it up, add 1, you get 3/2 power. Divide by 3/2, which is 2/3. Minus that to that, plus x. Okay, now I'm going to plug in 2. I don't know why this isn't working. 2 minus 1 is 1. 1 to that power is just 1. That's 2/3. I plug in 2 here. I get 4 divided by 2 is 2. We're subtracting 2, and then we're adding 2. Those go away. And now I'm going to plug in 1. I'm going to subtract everything from there, but that's 0. That's 1. That's 1/2. Wait. And 0. Nope, there it is. There it is. So this is a subtraction. So I should have 0 here minus 1/2, and maybe you found it before. This should be a minus because of this minus up here. I missed the minus here, so that's my mistake. Little minuses, negatives always get me. They always get me. It would probably happen this too, right? I see it in a lot of students' work, right? Just missing those little negatives can really just change the outcome of what we have. So that is probably it. Let's see now. How did that affect us? Because this is not that anymore. This is now 1 minus 1/2 is 1/2 that we are subtracting off. And then I build this up to have 1/6. So this is 4/6 minus 3/6. Yes, there's the 1/6. So There's the positive 1/6. I knew all of this because of that negative outcome, and I knew my area was not supposed to be negative. I knew something was off, and it was just this little negative I kept missing. So I guess the moral of the story there is watch your work and make sure that you understand, right, to check over your negatives. That's the biggest thing I would do if I was on a test. Is if I had a little bit of time left over on a problem, maybe I would just check over my negatives to make sure that my negatives were working, especially if I got something that didn't make sense like I did here. So understanding what numbers you're supposed to get out, whether positive or negative, really does help, right? So that did help me here. And then also, right, checking over your negatives. All right, I think that is it, because this is the last problem of the worksheet. So hope you enjoyed it, right? I hope you enjoyed even my mistakes. My mistakes hopefully help you see how I correct my mistakes, right? I'm by myself here, so I'm just going through helping myself, using technology to help myself find those little things, especially when I'm at home all alone, or come talk to your professor or a tutor or somebody out there that can help you. All right, everybody, take care. Professor Dre out. Nope, I didn't pause.